Now in this video lesson, I will be discussing about continuous charge distribution and Gauss law and some of its applications. So, continuous charge distribution. Here, generally we come across a charged body or charged surface where considering discrete charges is of no use. So if you say so many electrons are present on a body will be meaningless, because we will be dealing with objects or bodies having electric charge of the order of millicoulombs or microcoulombs. So in such cases, so we may consider the body to possess charges in a continuous manner. So you need not consider it as a discrete charge distribution. When we discuss about charges at atomic level or subatomic level, so in microscopic consideration, we may take that discrete concept of electrical charges. But for bodies having charges of this order, we may consider continuous charge distribution, so that the problem can be easily discussed or analyzed. Now, here we discuss about three types of charge distribution. Suppose if you have a line of charge, so let us suppose you have a line of charge of say some length L, and so it is having a charge Q. Then we define a quantity called total charge by total length. So this is defined as linear charge density. The unit is coulomb per meter. And if you consider any elemental part, small length, so delta L, then the charge of this elemental length of the wire, the charge can be calculated that elemental length multiplied with lambda. This is the charge of the element. So similarly, if you consider a surface, suppose there is a surface having the continuous charge distribution like this, and total charge is Q, and the area of the sheet is say some S. So this ratio, this quantity is defined as surface charge density. The unit is coulomb per meter square. So if you consider any small elemental area, say some delta S, this area element multiplied with the charge density gives the charge possessed by that much area. Similarly, in case of a body in terms of volume, so if the charge is distributed in the entire volume of the body, in such case the charge density is defined as total charge by total volume. So in any volume element delta V, when multiplied with the charge density, you will be getting the charge possessed in that small volume. So like this, we can define the charge densities: linear charge density, surface charge density, and volume charge density. Here, coulombs per cubic meter will be the unit. Okay, so we will make use of this while applying Gauss law. Okay, so next we will go for Gauss law. That is, Gauss law is related to the flux and the electric field. It relates the electric field and of course the electric flux. Already I told you what is that electric flux is. The electric field lines passing through unit area. So that through an area, how many field lines passes through, that we call it as actually electric flux. That flux density is defined as electric field intensity. So in any case, the flux density is taken as intensity. And now, first we will discuss what is Gauss law, and then we will go for its application. Gauss's law. See, let us consider a point charge Q, and let it be say some plus Q. At a distance R, I wanted to find out the electric field. So you can use Coulomb signal square law. Consider a sphere around this point charge with the R as radius. Now I select a small area element here. So let us suppose say some delta S. I want to find out the flux coming through this elemental area. So already we know flux is defined as the dot product of electric field strength and the area element. So that's what we know. Now here if you apply that concept, so elemental flux through the elemental area is given by E bar dot delta S bar. See, we know at every point on the sphere the electric field is constant because all the points are at the same distance, and you know that electric field has a spherical symmetry. Therefore, at every point the electric field strength is same, and this can be written as E delta S cos theta. But you know the normal drawn to the area element is in the direction of the electric field. Therefore, theta will be 0, hence this is equal to E dt delta S. And you know, to find out the total flux through this sphere around this point charge plus Q, you divide this entire sphere into small elements and then sum up the flux due to all such elements. In such case, total flux is given by sigma delta F delta phi. So that is nothing but sigma E into delta S. Also it can be written as, flux can be written as closed surface integral of E bar dot ds bar. So this is also okay. Both are one and the same. So if it is divided discrete areas, then you will use the sum up. If there is a variation, that is if the area element or the product is a continuously changing quantity, then means that we use that integral symbol. Where if the electric field is not constant at every point, in such case we use that integral method, and if the field is constant, then we use this summation method. So that is the difference between these two, but basically they give the same meaning. So that is equal to, let us suppose here the field is same at every point, hence E into, and your summation is for the surface area of the sphere. So what is the formula for surface area? It is the surface area formula is 4 pi r square, where r is the radius of the sphere. And from our Coulomb's law, the electric field strength is given by 1 by 4 pi epsilon naught Q by r square. So that is the formula for electric field strength. Now multiplied with 4 pi r square. So this 4, this 5 and this r square gets cancelled. What remains? Q by epsilon naught. That is the charge enclosed in the surface divided by epsilon naught. So the flux through the sphere, that spherical surface, is 1 by epsilon naught times the charge. So this is the mathematical form of Gauss law. So without actual proof, we are saying that the total electric flux through a closed surface is given by the 1 by epsilon naught times the net charge inside the closed surface. So this is actually known as Gauss's law. Now you have to take all the charges, whether they are positive or negative, enclosed in the surface. So if there are positive charges, take positive sign. If there are negative charges, you have to take negative sign. So you have to take the net charge inside the Gaussian surface, and this is how we can explain Gauss's law. Now, what is the importance of Gauss's law? So the importance of Gauss's law lies, it helps us to calculate electric field strength in the case of certain charge distributions having some sort of symmetry. So for charge distributions having symmetry, we can apply Gauss law and we can find out the electric field strength at a point due to the charge distribution. But we should keep certain points in mind while using this Gauss law. You see that the surface you are selecting around this charge distribution, we call that as Gaussian surface. Here, this surface we are calling it as a Gaussian surface. Now, this Gaussian surface should have some symmetry, then only you can easily calculate the electric field strength. So, while selecting this Gaussian surface, the surface may pass through the continuous charge distribution, but it should not pass through any discrete charges. So that is a very important point. So why the surface you are choosing should not pass through the discrete charges means the electric fields are not well defined near the discrete charges. That's why we should avoid, by selecting the Gaussian surface around the charge, that the surface should not pass through the Gaussian surface. That the Gaussian surface should not pass through the discrete charges. The another important point you must remember is the while calculating the electric flux. So you are getting the charge here. The charge is the total charge inside the surface, but the electric field, may be due to the charges present inside the surface or outside the surface. Okay, because when you relate these two equations, see, you can relate these two equations. That is, E bar dot ds bar is equal to Q by epsilon naught, or generally E bar is equal to, that is, sigma. So, or we can write like this: total E is equal to Q by epsilon naught into 1 by total area. That is what we get. So here on the left side you are getting the electric field strength, and on the right side, when you apply the Gauss law, you are getting the total charge. So the charge you are using in the formula is the total charge inside the closed surface or Gaussian surface, whereas the electric field strength is due to the electric field present due to the charges inside the surface or outside the surface. That is another point. Next one is you can apply Gauss law irrespective of size and shape of the Gaussian surface you are choosing. So it is independent of shape and size of that surface or the Gaussian surface you are choosing, and you can easily apply Gauss law if you have some symmetry for the charge distribution. Then another point is, since the electric flux depends on the square of the distance, here we derived this formula, Gauss law, we have shown that the flux is depending on the square of the distance of the area you are considering, surface area you are considering. So therefore, any wire which is similar to that of Coulomb's law, which is in which the field is or I can say electric force depends inversely on the square of the distance. Therefore, the Gauss law depends on Coulomb's inverse square law. Therefore, any violation in Gauss law will lead to violation in Coulomb's inverse square law. Okay, so these are some salient points one must remember regarding this Gauss law. Now,